And I want to finalize this lecture with a few remarks. If we recall that how we define the algebraic geometric code, we suppose that the Riemann space of a divisor G, the divisor we consider the functions from the Riemann space is supposed to be has disjoint support to get a meaningful images under the residue class maps. But if G is a divisor, if you consider a divisor G whose support is not disjoint from support of D, thanks to equivalence we consider, we can still define an algebraic geometric code. Algebraic geometric code. Is image of the Riemann space of G under the evaluation map D. As follows. So in this case, we can choose an equivalent divisor G, and G prime uniquely, which is defined which can be well defined up to equivalence, which we consider proposition 2 to 14. But this unique choice is unique up to equivalence. And as I mentioned before, this equivalence, it preserves the dimension and the minimum distance, but it doesn't preserve some other important structures like automorphism groups. I'm not going to give a counterexample, but just for the moment, simply, I just want to explain how we can define an automorphism group of AG codes. But for the details, I can recommend you to check the section 8.3. So to define the automorphism group of algebraic geometric codes, first let me try to define what does automorphism mean for a linear code. So for the automorphism, what we expect is to preserve some structures. And for the coding case, we first consider the symmetric group Sn, so whose elements are the permutations of the sets size n. And indeed, we can see that this symmetric group, we can define indeed an action of this symmetric group on the vector space Fq to the n. And indeed, this action is defined on the coordinates by permuting the positions of the coordinates for a code over C. This is C. Let me use this notation for the indices from C1 up to Cn. And indeed, with respect to this permutation, the automorphism group of a linear code will be group of the permutations which preserves the code, which fixes the code. So in other words, the automorphism group of a linear code C is defined by the automorphisms defined by the permutations which fixes the linear code C. And obviously, the automorphism of a linear code is a subgroup of permutation group because the identity is in Sn, because the identity function always fixes the code. And if we have a permutation from automorphism group of C, so that means that fixes C, and we can also easily see that its inverses also fixes C. And finally, if we consider two permutations, such that C is invariant under these permutations, obviously its composition will be an element in the automorphism group of C. So it shows us we have a group structure. And in the research direction, of course, the linear codes with non-trivial automorphism groups are interesting. Maybe a nice exercise here for the cyclic codes. What is the automorphism group? When say cyclic. So the first case can be a cyclic group of finite degree. And for the function field case, the last thing I want to mention that as an advanced topic, you would see that you can see that the automorphisms in the particular algebraic geometric codes, automorphisms of the function fields indeed produces the automorphisms of the algebraic geometric codes. So if you want to work with a linear code which has rich automorphism group structure, the one thing can be checked to check the codes which are produced from algebraic function fields that has large automorphism groups. So on Thursday, we will consider some survey for algebraic geometric codes, which are produced by algebraic function fields of low genus, particularly for elliptic and hyperelliptic case.